Hello everyone, my name is Oscar Chu, and I'm honored to present our research paper titled Understanding and Mitigating Spurious Correlations in Text Classification with Neighborhood Analysis. I am joined by my co-authors, Xuantian Lin, Kaiwei Chang, and Guanhao Huang. Together, we represent National Taiwan University, University of California, Los Angeles, and University of Illinois Urbana-Champaign. Let's begin by examining a simplified dataset. This movie sucks. Negative. All of this pointless crap should have been cut out. Negative. The movie was horrible. Negative. Very happy about the purchase. Positive. The word movie in red is an example of spurious tokens. Tokens that are not causally related to the labels, while the words in greens are genuine tokens, which are causally related to the labels. When facing this training set, our language models have two choices. First, they can understand the semantics of the whole sentence, or second, they simply predict negative whenever the word movie appears in the sentence. Unfortunately, it is known that language models often choose the second option. Relying on spurious correlations poses a significant danger, as models built on such correlations are prone to failure in real-world applications. While these models may perform well on benchmark datasets where spurious correlations hold, they often falter when faced with new, unseen data. In this work, we aim to answer these research questions. First, why do language models rely on spurious tokens in text classification tests? Second, how do we robustify NLP models against spurious correlations? And finally, how do we detect those spurious tokens for better explainability? To study the problem under a controlled environment, we inject spurious tokens into two text classification datasets, Amazon binary and Jigsaw. We associate book with positive labels, movie with negative labels, and people with toxic labels. These tokens are chosen because they appear frequently in the dataset. We obtain our DE bias by subsampling the original datasets. Then we obtain a clean DE unbiased by randomly sampling examples of the same size as DE bias. Let's take our first look at what occurs during fine-tuning. We look into the nearest neighbors of these spurious tokens in the embedding space. Before fine-tuning, these tokens are surrounded by tokens with similar semantics. For example, movie is close to film and music. Book is close to library. However, after we fine-tune the language model, we observe that movie is now similar to negative words such as fool. Book is similar to positive words such as benefited. This hints us the mechanism of how models capture spurious correlations. The word movie is now perceived as a truly negative word from the model's perspective. In other words, models may have forgotten the original meaning of the words. Now we introduce our neighborhood analysis framework. To determine whether the meaning of a token has been lost, we examine its nearest neighbors. First, we extract the representation of every token in a vocabulary. Then we collect the nearest neighbors of the target token in the embedding space. We will then utilize a reference model F star, which can be trained on either D unbiased or D bias. F star will output a soft label for each token, and the spurious score is defined as above. The spurious score is essentially the average distance between the neighbors before and after fine-tuning. After performing neighborhood analysis on the selected spurious tokens, We have these two diagrams illustrating the embedding space before and after fine-tuning. The results matches our earlier observation, where the spurious tokens are aligned with the genuine tokens during fine-tuning. As we have determined using a neighborhood analysis that the heart of the problem is the misalignment of spurious tokens and the genuine tokens in the language model, we propose our mitigation method, NFL, which stands for Don't Forget Your Language. Our main motivation is to leverage off-the-shelf language models to guide the trained language models during fine-tuning, restricting drastic changes in the embedding space. Off-the-shelf pre-trained language models can serve as effective safeguards because they, by definitions, are not exposed to spurious correlations. NFL constitutes a family of regularization methods, where each variant either freezes portions of parameters or constrains weight changes with regularization terms. As you can see in the diagrams on the left, NFL can effectively prevent misalignment and therefore offers great protection to the models. The table on the right also shows that Robotar trained with NFL achieves lower spurious score. We compare NFL with DFR, which requires additional clean dataset, and also the ideal model, which the model is directly trained on clean data. While standard fine-tuning exhibits random guess accuracy, NFL enjoys low degradation and high robust accuracy, even without any additional data. Our proposed spurious score can also be used to detect naturally occurring spurious tokens in real-world datasets. Prior approaches require additional resources such as human annotated examples or datasets from different domains for the same test. On the contrary, our spurious score achieves similar precision without requiring those resources. Finally, we conclude our presentation by answering the research questions. First, language models rely on spurious tokens in text classification because the representations of spurious tokens and genuine tokens are aligned during fine-tuning. Second, we can robustify NLP models against spurious correlation by preserving the semantic knowledge in pre-trained language models through NFL. Third, spurious tokens can be detected using our proposed spurious score. Thank you for your attention.